Hello there, calculus. So today we are going to talk about what is often called the fundamental theorem of calculus, part one, technically. The one we did before, where we did the integral evaluation theorem, is often considered part two, and this is considered part one. So you're probably thinking, wait a second, why do we do part two first? Honestly, because I think it just makes more sense when you're trying to piece it together in your head. But that's just me. And you know what? I'm the teacher, so I get to do what I want. Haha, power. No, really, that's not why. I just really think it makes more sense. Um, and I wanted to make sure it stuck with you. So, in part two of the fundamental theorem of calculus, we learned that in order to evaluate a definite integral, you take the antiderivative, plug in the bound, and subtract. So, what that implies is that the integral and the derivative are opposites. They are inverse operations. The derivative goes one way, the integral goes the other way. It's the antiderivative. So the fundamental theorem part one really builds on that fact and says, wait a second, if the derivative and the integral are inverses, doesn't that mean if you do them both at the same time, they cancel out? And the answer is yes. Yes, they do. So that's what we're going to get at today in some of the consequences or dominoes that fall when you use that idea that derivatives and integrals are inverse operations. So let's get to it. I'm going to skip over the thing at the top for a second and really show you how this works. And then I will go back and explain what the integral evaluation theorem part one kind of means. So let's do that. So number one here says, what if you were going to take d dx of the integral from 3 to x of 1 plus t squared dt? Well, there's like an implied bracket here that says do this first. Okay, if I want to evaluate a definite integral, an integral with limits of integration, I would take the antiderivative, plug in the bounds, and subtract. So I'm going to do that. So I want to take the derivative of 1 plus t squared with respect to t. So the antiderivative of 1 with respect to t would be t, and the antiderivative of t squared would be 1/3 t cubed. Just doing backwards power rule there. And then I'm supposed to evaluate that from 3 to x, and when I'm done doing that, I'm going to take the derivative with respect to x. Okay, so that means I'm going to have x plus 1/3 x cubed minus 3 plus 1/3 3 cubed. Okay, so that's really going to be x plus 1/3 x cubed, and then 3 cubed is 27, a third of 27 is 9, 9 plus 3 is 12, so minus 12. And then when I take the derivative of that with respect to x, the derivative of x is 1. The derivative of 1/3 x cubed is going to be x squared, and the derivative of 12 is going to be 0. So I get 1 plus x squared. So the derivative with respect to x of the integral from 3 to x of 1 plus t squared dt is 1 plus x squared. Okay, well, what do you notice? Well, what I notice is that I started with 1 plus t squared. I ended with 1 plus x squared. I was evaluating the integral of 1 plus t squared as an x, and then that x got put in. So what really happened? Well, what really happened is this. When I took the derivative, when I took the derivative of the integral, what basically happened is the derivative and the integral canceled, and instead of having 1 plus t squared, I now have 1 plus x squared. What happens when you have an integral set up like this, and then you differentiate the integral, is your limit of integration just kind of drops down in there. And you might be thinking, but wait, Mrs. Weber, there's 2 limits of integration. What about the 3? Yeah, whatever, I don't care. Why don't I care? Because I'm taking the derivative with respect to x, and when I plug that 3 in, it's going to become a number. And then when I take the derivative with respect to x of a number, I get 0. So this 3 just disappears. It doesn't matter. All right? So now let's come up here. The rule itself for part one of the fundamental theorem is the derivative with respect to x of the integral from a to x, where a is any constant, of f of t dt is f of x. And again, what's really happening is the derivative and the integral cancel. And then that x just replaces the t. That's it. So let's go through here. What if I did it for number 2? Well, I'm taking the derivative with respect to x of the integral from a to x of sine 3t dt. So the integral and the derivative cancel. And this x goes bloop right in for the t. And I get the sine of 3x. The dt goes away because when the integral goes away, the integral and the differential are really like part of some bookends. So when one part cancels, so does the other one. And there's your answer. That's it. You don't have to show any work. You just have to realize that derivatives and integrals are opposites, and now it's in terms of x instead of t. Same thing over here. I've got the integral from a to x of the square root of t dt. The derivative and the integral cancel. The x replaces the t. That's it. What if I had the integral of d dx from a to b of f of t dt? You want to be careful here because you want to realize that, wait a second, I don't have any x's. So when I evaluate the integral from a to b of f of t dt, I'm going to get a number. So this whole inside ends up being d dx of a number, and the derivative of a number is just going to be 0. So you do need to look at what are you differentiating. Is it the integral from a to x? If so, use the rule. If not, don't use the rule and think about it a little bit more. Okay, couple more down here. On number 4, I want a different color. Gray is boring. Let's do orange. The integral from a to x, d dx. Okay, I have that thing again. The derivative and the integral cancel. The x drops in for the t. 2x minus 1. Now, also, if your integral is not in terms of t and it's in terms of like y or r or theta, it doesn't matter. Okay, whatever this variable is drops in for whatever variable your integrand is in terms of. Okay, it's a dummy variable anyway. So then when I get to number 5 here, d dx, a to x, okay, I got the same thing. Derivative and the integral cancel. The x drops in here, ln x squared. That's it. Number 6, whoa, I've got like an f prime in there. I don't care. I don't care what your integrand looks like. If you're taking the derivative of an integral, your derivative and your integral cancel. Your limit of integration replaces the letter in the integrand. So this is just going to be x times f prime of x. Uh-oh. I got d dx, but now instead of my integral being from a to x, it's the integral from x to a. Remember that really stupid joke I told you guys a long time ago about the mathematician setting the dumpster on fire because he wanted to reduce something to a previously solved problem? Yeah, that's what we're going to do here. If I look at this, it doesn't look like what I'm used to. That's okay. I can fix that. I can realize that, you know what? I'm really taking d dx of the negation of the integral from a to x of sine of t dt. Because remember that rule about integrals that you can flip-flop the limits of integration as long as you negate the integral. So I'm going to do that and say the integral from a to x is the negation of the integral from x to a. So now when I go to take the derivative, I can say, oh, okay. So when I take the derivative of that, the derivative and the integral cancel. The x drops in for the t, and I have negative sine x. Da-da-da. So there's the front. That's it. Don't make it any harder on yourself. Derivatives and integrals are opposites. But what happens on the back here when I have to do the fundamental theorem of calculus and I don't just have an x, I have like an x squared or an x cubed or a sine x. Let's see what happens there. I'm going to do a lot of what I did on the front where I go through and evaluate this and show you the long way and then say, hey, let's notice what happens here. So I'm going to do that. And again, I'm going to change colors because I feel like it. Green. So now I want the integral of d dx, the integral from negative pi to x squared of cosine t dt. Okay, so what's the antiderivative of cosine? Whose derivative equals cosine? Well, Whose derivative equals cosine? That's going to be sine is the antiderivative of cosine. And I'm evaluating that from negative pi to x squared. And then I'm going to take that and differentiate it. So that's going to be d dx of sine of x squared minus sine of negative pi. And that's going to be d dx of sine of x squared. And the sine of pi is 0. Okay, so then the derivative of sine x squared would be a chain rule. Derivative of the outside, keep the inside, times the derivative of the inside. Okay, so my answer is that the derivative of this integral ends up being cosine x squared times 2x. So cosine t, when integrated to x squared and then differentiated, becomes cosine x squared times 2x. What happened? Well, what happened is this. Exactly what I think would happen based on the front. The integrand gets evaluated at the limit of integration, so the x squared drops in for the t. But then I also have a 2x, and 2x is the derivative of x squared. So when you are differentiating an integral and your limits of integration aren't just an x, they're a function of x, you still drop the limit of integration in for t, but then you also multiply by the derivative of that limit of integration. Okay, so this thing gets dropped in, and then this is the derivative of x squared. That's it though. So let's use that shortcut now. If you want to take the derivative of an integral, you're going to drop the limit of integration in for t, but you're also going to multiply by the derivative of that limit of integration, by the derivative of the bound. So this becomes secant squared x cubed times the derivative of x cubed, which is 3x squared. Let's do it again. D dx, the integral of 0.5 to sine x of root 2t dt. I don't care if it's trig. Whatever function of x this is, the derivative and the integral cancel. This thing drops in, and so I have the square root of 2 sine x times the derivative of sine x. Well, what if the x is on the bottom? Well, we said if the x is on the bottom, that's really just negating what would happen if the x was on top. So if I want to take the derivative of 2x to 3, the integral of 1 over t squared minus 5, the same thing's going to happen. This 2x is going to go in for the t squared. I'm just going to negate my answer. So it's going to be 1 over 2x squared minus 5, negated because that 2x was on the bottom, and I need to multiply by the derivative of 2x, which is 2. So negative 2 over 4x squared minus 5. Same thing down here. All right. So if I have this from 5x squared to 0, it's the same as if I negated it and put the 5x squared here and the 0 down there. So I'm just going to negate my answer, plug 5x squared in for t. So negative 3 over 5, forgot my minus, 5 minus 5x squared squared times the derivative of 5x squared, which is 10x. So I dumped the limit of integration in for t, I negated it, and I multiplied by the derivative of that limit of integration. And let's make this look a little bit nicer. So that would become a positive, and 3 times 10x would be 30x over 5 minus 25x to the fourth. And if I really wanted to simplify it more, which I don't have to, but I feel like it this morning, I'm going to do that. What if there's 2 of them? Okay, going to set the dumpster on fire again. So I got 2. I don't have an A that I can ignore again. That's okay. I'll make one up. Watch this. the integral of x squared to x of something. Why did I write an x and a 2 up there? Let's try that again. The integral from x squared to x of something is the same as the integral from x squared to 0 plus the integral from 0 to x. I can use that idea that if you integrate from 1 to 2 and then from 2 to 3, it's the same as integrating from 1 to 3. So if I have an integral that has two limits of integration with x's in them, I can think about it as two separate integrals. Where if I'm taking the derivative of this one, it'd be like taking the derivative of each of these. So what's that really going to mean? It's going to mean that you plug in both limits of integration and then subtract. So my derivative and my integral cancel. X gets dropped in here. So I'm going to have the square root of x plus x squared minus x squared gets plugged in here. But since x squared has a derivative other than 1, I need to multiply that second thing by 2x. So you're still dropping in the limits of integration and then multiplying by their derivative. Okay, if you want to think about it, I plugged x in and then multiplied by its derivative, subtract, plug x squared in, and multiply by its derivative. Let's do it one more time and I'm done. Here's another one with dual limits of integration. So derivative and the integral cancel and both of these things get plugged in. So I have ln x squared times the derivative of x squared minus ln sine x times the derivative of sine x. And that's it. Derivatives and integrals are opposites, so when you differentiate them, your integrand pops right out. It's kind of like squaring a square root in a lot of ways. And now I'm done. So I hope everybody's having a good day. I hope you continue to have a good day, and we will talk again soon.